Okay, we have a time constraint, so I start quickly. I am Antonio Cuni. I am a PyPy core developer, so that's why I am into JIT Compiler. I want to show you that JIT Compiler is usually a complex piece of technology, but it's not so complex. I mean, you can write a very simple one in a short period of time. So let's try. We will write a JIT Compiler for a subset of Python, like syntax of Python, but not many features. So we will assume all the variables to be of float type. So we only have that only the basic operations, and I am cheating a bit because we use PitchPy, which is a Python module to encode assembly instruction. I don't start from scratch completely because else it takes much more than 30 minutes, but this is a library that you can just use. And the disclaimer is that really I wanted to do this talk, but I never wrote any single line of assembly before doing it. So what I did was to compile things with GCC and see what is the code which it generates and learn from it. So, for example, let's start. So, no, it's yes. So, for example, we start from this, and we see that this is a very simple function which is written in C and adds two double numbers. So, let's see. We can compile it with GCC. We can see what is the code generated by GCC, and so this is the assembly. Do you see it? Yeah. Okay. I don't see the mouse. Yes, here. See, this is the assembly code which is generated for this. So let's try to execute it from Python. So for example, we start. These are the bytes which I just showed you in the object dump. And in order to execute it, we need to allocate a buffer and mark the buffer as executable so that we can write at runtime the assembly in it and then tell Python to execute it as it was a compiled function. And for this, you need to use a map. And in particular, it's important to pass this flag to a map, which says that you can execute this page. And then we need a way to cast it to a native function and use CFFI for it. So, for example, now we can cast this buffer to the type fn2, which is the type of our function which takes 2 arguments. And I hope that it should just work. Let's try it. So I try to add 2 and 3, and if I execute it, it doesn't work. Okay, of course I tried it 5 minutes ago and it worked, but yes, let's avoid the completely live thing and start to look at the tests. These are the tests that we will implement during this talk. So the first thing we want to try is to have this compiled function. This is the same code as before. We want to have this compiled function to which we can pass the number of arguments and the code, the assembly code, and check that if we pass the arguments, it works. So I think I'm cheating because I have some code which is just, yes, commented. Later it will be live. It was more live, but I didn't have enough time to do everything. So this is exactly the same code as before. Yes, you see, it is nothing like for the compiling function, we allocate the buffer, we copy the buffer, we copy the code inside the buffer, and we cast it, and then when we call this function, we call the function pointer behind it. Let's see if our test is working. Okay, good. We are making some progress. The next thing we need in our test, at some point, we want to write a compiler, and we need a register allocator. So basically, the idea of the JIT we are writing is that every variable will be stored in a register. And so we need a way to associate variables to register. And in a real compiler, it does a lot of logic to make sure that the used variables are in a register, which is faster. If you need more variables than the register available, you need to spill them and to reload the value when it's needed, and etc. But in this simple example, we just cheat, and basically we just allow as many variables as the number of registers we have in the CPU. So every variable will be stored in XMM 0, 1, and 2, and etc. And here you see in this test that if you try to allocate more than 15 variables, you just get a not implemented error. This is for like how to write a JIT compiler in 1 year, not in 30 minutes. So, and again, here I am a bit cheating because I didn't want to spend too much time writing all this thing, but oops. So okay, so let's write a register allocator, something that we can call and allocate registers. So we maintain a list of available registers, which is the reverse of this register list that we have here, that it's all the registers available we have. Then we have this dictionary. We use a default dict so that every time we get a new variable, it will call this allocate method, which will so we try to pop a register from the list that we have, and when there is no more items on it, we just raise not implemented error, and that's it. And then, of course, when we try to get one register, and that should be. And the nice thing is that here you can use default dict to maintain the state. So whenever you try to get a new register, a new variable that you have not allocated yet, it's calling allocate. So you pop from the list and etc. Let's see if it works. And it's working. Okay, so this was what needed to start. But now let's start the real funny and interesting thing. So this is the first test I want to do. So I want to compile a function, and which does nothing, but I want to make sure that our JIT compiler can start. So in a normal compiler, you need all the steps to start from the source code, which is a sequence of characters, parse it, make an abstract syntax tree, and then compile it to native code. But here, I don't have the time to do all the parsing because it's a complex thing. So I am reusing or abusing the Python Ast Compiler. So in Python, you can take some source code as a string and tell Python to compile it to an abstract syntax tree, and now I will show you very very soon how does it. And then we can use this data structure to visit and to emit the code that we want. So we are writing an Ast compiler, which is something which parse the source code that we pass to it inside a tree, and then I have this nice helper which will help us to visualize the tree in a graphical way. Then I don't want to spend too much time on writing this method, so let's just copy it. Okay, we will use the visitor pattern. Okay, the tree is a tree that I will show you very soon, and then I want to be able to call a different method depending on the type of the node of the tree, and depending on what type is it, do something to emit the source code. So here I am just using a generic visit function that I can pass a generic node. It does some introspection to look the name of the node, get the corresponding method that I'm about to write now, and call it. So let's go back to our test. See, I pass the source code and I call compile and try to execute it. Let's try to run the test. Okay, I don't have the method compile. Let's write it. Compile doesn't take anything, and what I want to do is start to visit the tree from here. And also, let's see how it looks like, this tree. So here, I stop, and I can my self.show self.tree, see if it works. Yes. Oh, I forgot to start the timer. Yes. How many minutes did it pass so far? Something like this. Okay, so this is the tree. This is the AS tree that Python generated for us. You can see that everything starts from module, then it contains a function def, which is our the function we are compiling. The function is named foo. It has no arguments, and it has one statement which is pass. So let's try to implement all of it. If I try to visit, I will soon get an error because now it's trying to call the method module, which is not there. So def module, which takes a node. And what I want to do is I want to visit all the children of the module recursively. And then the module, which contains a function def. And what do we want to do? Well, we want to check that we are not already compiling a function, because this JIT compiler support only a function at a time. Then we want to extract the argument names. But this is just unpacking the attributes of the AST tree. And then I'm going to just copy and paste this function again because I don't have too much time. And then once I create this function, like I initialize the assembler, the ISM attribute which contains my assembler function, which I'm going to compile, I want to, again, thank you. This is not pair program, this is like hundreds of programming or something. So I want again to visit recursively all the children of these, and then I want to, by default, if nothing happens, I want to return 0. So what I do is to use this ASM object, which let me to generate assembly code on the fly, and that should be. So this is like a way to load the number 0 in the XMM register number 0, which is the one which is used by the x86 calling conversion to return the value. So now we need to copy this new func module. And what I'm doing here inside is to initialize this ISM attribute, which is our function assembler, which contains all the assembly code we are generating. Then I initialize the register allocator. Then I allocate a register for all the arguments, because the calling convention says that the first argument is in XMM0, the second is XMM1, and so far, and so on. So by doing this, I am ensuring that the arguments are in the correct register. And then I also allocate two temporary registers that I will use later. So let's see how it goes, our test. OK, so I'm compiling the function, but I didn't implement the pass. The pass is really this node of the AS3. So let's implement it, self node. And of course, it doesn't need to do anything. I think that, OK, so we are here. We managed to visit all the tree that we have, and let's do something with it. So I go back to the compile function, and now that I have emitted all the assembler I want, I can just, well, call this method, which returns the assembler I generated as a string that I can then pass to the compiler function that I showed you earlier. And let's try, and it passed. So we managed to have the empty skeleton of our JIT. By doing this, we can compile a function which does nothing, but it's already generating some assembler code, and it's writing it to the memory with the correct permission. It's loading it at runtime. It's executing and just return 0, and it's already something. So let's see the next. That's simple. It's like before, but now we want to return something. We want to return a constant, a number, and we check that when we call this function, we will get this result. So let's try. And OK, we have not implemented the statement return, because if I show you def return self node, let's stop it and see how it looks like. Yes. So see, in red is the current node that we are visiting. So it's like earlier, but now this is the current node. And return is a node which contains a number, which is an expression, which contains a constant, which is 100. So let's implement all of them one after the other. So OK, so we need a way to evaluate expression. Right now, it's a simple expression, just 100, it's a constant. But maybe later we will have a complex expression with a lot of binary operations, parentheses, and etc. So the idea is to maintain a stack of value. When you evaluate an expression, you are taking the operands from the stack, and you are pushing the result on top of the stack again. So for return, and when you visit a node in our compiler, the node emits code which puts the result on the stack. So for returning, I want to visit node.value, which is this num you see here. And then once I visited it, I want to pop it from the stack and put it inside XMM0, which is the register for returning, and then generate a ret. And then I need the num. So I want to evaluate this node, which means I want to take the constant, which is inside the node.n, and put it inside the register, and then I want to push the register on top of the stack, so that later the return can pop it and return it from the assembler. So what I do here is to use this move SD, which is move scalar double, and the target is my temporary register 0. I want a constant, which is node.n, which is 100 in our example, and then I push to the stack, and then the return will pop from it, and so on. So let's see. And I think push SD. It's a typo. You didn't notice it. Too bad for you. No cookie. OK, it works. So let's go to the next test. And here, I think that this should maybe just work. OK, no, this is not going to work out of the box, because the difference is that here we were returning a number, so we have the num node, and here we are returning an argument, which is a name node. So we need to teach our JIT how to handle the name node, which means how to load a variable which we know it's stored in a register. So if you remember, we use the register allocator, and the name of the variable is inside the attribute id. So self.asm.push sd reg. So we are getting the register, and we are pushing it on the stack immediately. And it just works. So you see, starting it's a bit complicated, but once you are started implementing all the new features, it becomes easier and easier. And now, yes, something a bit more complex. Let's do operation. I want to add two numbers. So what's going to do here is that, OK, let me show you let me show you the tree, which maybe it's easier to discuss. I see, because it's running all the tests. Yes. So this is the tree we are compiling now. You see the usual return. Now you return a binop. The binop has an attribute which contains the name of the operation, and the two expressions, which are name of A and name of B. So our code will push on the stack A, the register containing A, push on the stack the register containing B, pop both of them to add them, push the result on the stack, and then the return will pop it and return. I mean, so this is the way you evaluate all the expression, pushing and popping of the stack. And this is not our real compiler work, because it's inefficient. A real compiler would use temporary register to avoid pushing and popping to the stack. but it's much simpler to generate a code this way, and we will see that it's still kind of efficient. So let's implement this binop. So def binop self node. So we want to visit the left. We want to visit the right operand. And these are pushing the value on the stack. We want to pop the first operand, the second, I mean the rightmost in the temporary one. We want to pop in temporary 0. And then we want to check that node.op. Okay, let's see, like op name, node.op.class.name.upper. Okay, this, oops. This is just a complex way to know which is the operation, and in this case will be uppercase add. So assert op name equal to add. And then I want to use self.asm.add scalar double, which is the assembly instruction we want to use, and we want to add temp 0 and temp 1. And now we have the result inside temp 0. So this assembly instruction basically does temp 0 plus equal temp 1. So we want to push temp 0 to the stack. Let's see if it works. It works. I didn't expect it because I was sure to have done some mistake, stupid mistake, but apparently I didn't. I mean, I have time to do a more stupid mistake later. I mean, so let's try to do more complex tests. So now I have a test that does all the other possible operations, like minus, pair, times, division, and with parentheses. So we also check that our pushing and popping of arguments is working correctly for the precedence of operator. Let's run the test. Okay, I have an assertion error because so far I implemented only the case for add. So I want to do more, and yes, I just copy and paste. Easier. So this is the final version, and see, I use a dictionary to map every operation to the correct assembly operation, but it is really the same as before. And it works. So let's see again. I want to assign something to a variable. So here I'm going to compile b equal to a plus 1. And OK, I need to implement the node assign of the AST. So let's do it. Def assign self node. Okay, in Python you can have more than one assign. Like you can type A equal B equal C and etc. But here I want to handle only the simple case in which I have only one target. So I check that I have only one target. The var name you fish inside the node, and it's something like this. So what I need to do, I need to know which register to use. So it's here, self.regs.get var name. And then I want to visit the value of the node. Node.value is the expression. So in my AST will be a plus 1. So it visits, and at the end it push the value on top of the stack. So what I do now, I move the value from the top of the stack. I pop it to temp 0, and then I move I move temp 0 to the actual register which contains my value. Thank you. Pop. Asm.pop. Yes, exactly. Okay. So, and now, okay, to have a real language, so far we are just evaluating expression. The harder part are the if and the while. Like I need at least an if and a while loop in order to be able to compute anything useful. So let's do the if. So I want to check, for example, that if a minus 0, okay, this is just to do the absolute value. I had to use 0 minus a, because else minus a is a unary operation, and I didn't feel like to implement also this, so it's just cheating again, but yes. I don't think I have time to show you live the implementation of if, so I just copy it. And I copy also the while I remit it. So the idea of the if is that we want to generate this kind of code. So we want to do the test, to say, and if the test it works, it passes, it's true, then we go to the 10 part of the if. Else we go to the end. So basically we are skipping the if. We are not implementing the else. And inside the 10 label, we do the body of the if. So again, here we are doing the same as before. So you see, you have asm.label, which is like we are pre-declaring a label which will be defined later. So I visit the operation, which is the compare, which we implement later as a visitor of the node. Then we handle only the case of less than, which we implement as the jump below assembler instruction. So if it's less than, we go to the 10 label, else we jump to the end, and here I declare that in this position of the assembler, it's where my label, my 10 part is it, and then I visit the body of the node, which contains the 10, 3. And then at the end, I just put the label for the end. And the compare operation is, again, is very similar to what I showed you earlier. So I visit the left, I visit the right, I pop the two values, I compare them using this assembly instruction, which I don't remember what is the shortcut for. Com is for compare, SD is for scalar double, and U and I have no idea. And I really just copy and paste from the GCC output, and that's it. And the while is basically the same. It's very similar. I am not going to show you the details because I don't have time. But you see that we are generating this kind of code. So at the beginning we do the test. If the test passes, we go to the body, and at the end of the body we go up again to the begin. And when the test is not passing, we go to the end. And then the program continue. And it's really the same. So let's see if everything passes. Yes. So the latest thing I want to test is that, okay, now I have a compiler which more or less does everything. Okay, I also have the test while. And I want to use a nice API so that my user can compile it easily. So I write a decorator, which I can decorate, which I can use to decorate a function and get the compiled function. So let's write it. So if we do the test, well, I don't have the function compile, so let's write it. Def compile fn. Okay, I don't think I have time. Let's copy again. Sorry. Oh, I don't even. Oh, okay, I don't even have here. That's because, yes. Okay, I really need to implement it now, then, yes. So what I want to do is to get the source code, and I can do it with inspect.getSource of fn, then I want to compile it with Ast Compiler of source, and I want to comp.compile. I think something like this. Oh, you know, the inspect is a standard module which get you to you can use to get the source code of a given callable. Ooh, it works. Oh, this I'm surprised. Okay, so now we have something which works, and let's do a benchmark. This is a dummy, and not really. It's not real-world way of computing the digits of p. It's very inefficient, but well, it's something which is simple enough to be compiled by our JIT compiler. So here I have this benchmark, and I first run the function on CPython, then I compile it here, you see. I compile it with my JIT using the decorator, and then I run it, and let's see the performance. Yes, you see it works. It gives the very same result, so at least it's not so buggy, and it's much faster. I mean, it's very simple and etc. But you see, it's like 10 times faster than CPython. And okay, then we can also compare with a real JIT compiler, which is, for example, PyPy. And PyPy is much faster again, but that's because PyPy really managed to produce optimized code without having all this pop and push from the stack and etc. But basically, that's it. So yes, as you see, the skeleton of a JIT compiler is not rocket science. Making a JIT compiler which is efficient and works for all the cases and etc. It's not rocket science, but it's closer. And well, that's it basically. I didn't start the timer. You should have told me. I still have 22 minutes left.
No, you have started, but it's finished already.
Okay.
So you have 5 minutes more.
Okay.
Some question? If it works? Just
why faster than CPython?
Because doing numerical operation on CPython I mean, CPython to numerical operation does a lot of things. Like, for example, an object in Python is represented using a structure on the heap. So whenever you do 1 plus 2, what you do is to take the object from the heap, which is a structure which contains many things, including the actual value. You fish it, you put in the register. You fish it from the other operand, you put in the register. Then you check what are the types, and it's really like hundreds and hundreds of CPU instructions, and then at the end, you get the value in the register. And then you construct a temporary object to hold it, like the float object or the int object or whatever. And this is just for doing one single operation. And for doing an if, it's again hundreds and hundreds of CPU instructions. So my JIT is inefficient because maybe it uses like 5 instructions instead of 1, but it's 5 to 1, it's not 5 to hundreds. So, I mean, it's a general question of why Python is slow as an interpreted language, and it's why PyPy is faster also.
1 second.
Just to check if I understood correctly, you in your compiled code, you're just returning a number on the register. You're not returning an object.
Yeah, yes.
You don't have.
Yes, but then basically, okay, then of course I have, at the end I get a Python object, a Python float object, but this is done by CFFI. Because if you look here, where is it, jit.py, here to execute the function, I rely on CFFI to call an external a C function or assembly function. And CFFI has all the logic inside to know that this function returns a value in XMM0, and then it needs to fish it from there and return a nice Python object which I can use later.
But is it done only at the end of the compiling?
Yes.
Or
Yeah, it's only at the end.
When you are running the compiled function, you just use numbers in the register,
Yes.
not Python.
Yes.
Okay.
During the computation of P, in the example, you never allocate any Python object. You allocate only the result at the end. It is.
Could you remind us where all the assembly manipulation code came from? Was that written off screen, or was that the PeachPy repo you mentioned?
What is
everything in self.asms or move,
yes.
scalar double, all of these pop, all these sorts of things?
I have this module here, which is just a small layer on top of PeachPy, just to make it to make it easier to write. But basically, with PeachPy, you really can write assembly function by writing them as I wrote. Here, I just modified it so that I have a nice ASM object, and when I do a get out, so I move SD, it fishes in and takes the instruction from PeachPy and execute it. But this is just because it was easier to test and etc. But PeachPy is a nice library you can use to generate assembler code like this. So the only caveat is that the released version of PeachPy doesn't really work. You should use the Git version. But yes, apart from it, it's here, requirements.
Perfect.
Hi. Thanks for the talk. I want to ask the question not about your compiler, but about the PyPy. Well, your compiler is much more faster because it operates on the numbers. But what about the PyPy? Why is it much faster than the C?
Well, because basically PyPy under the hood managed to take the Python source code and generate something which is similar in spirit to what my toy JIT compiler does. So PyPy, when you execute a Python function on PyPy, it notices that you are doing this loop, and in this loop, this variable are of type float. So it generates code which use the XMM register as I did. And it never allocates temporary object or so, and it never had to check that what are the type of the operands again and again, because it knows, because, and then of course, my Python is a complex language, so PyPy implements the full Python, so you have to insert what we call guards to check that if by chance you pass something of another type, like an integer, then you need to use another assembly code, because the assembly of adding two integers or two floats is different. So it does all this thing under the hood. But the real thing is that if you look at the code generated by PyPy, it's not so much different than the code that I generated now. And then it's faster, PyPy is faster than mine because it's more optimized, so it knows when to remove push and pop from the stack, when you use temporary register to hold variables better than what I do, but yes.
So I think we finished for the morning. So thank you, and